In this module, let us study about colloids. Substances like milk, butter, gelatin, mayonnaise, muddy water, and colored glass are examples of colloids. Colloids play an important role in interface science and in the fields of energy, food, mineral processing, pharmaceuticals, and environment. Colloids are one of the three major types of mixtures, the other two being solutions and suspensions. The three types of mixtures are distinguished by the size of the constituent particles. You already know that solutions are homogeneous systems in which the diameter of the solute is less than 10 to the power minus 9 meters. These particles are not visible to the naked eye. Common salt in water is an example of a true solution. On the other hand, a suspension is a heterogeneous system. The particle size of the molecules in a suspension is more than 10 to the power minus 6 meters. These particles can be seen with the naked eye. Sand in water is an example of suspension. Colloids are mixtures whose particles are larger than the particles of a solution but smaller than the particles of a suspension. The suspended particles in a colloid are small enough to settle down due to gravity. Thus, colloid represents an important and a large group of systems intermediate between solutions and suspensions. Therefore, a colloid is a heterogeneous solution in which the particle size ranges from 10 to the power minus 9 to 10 to the power minus 6 meters. These particles are not visible to the naked eye but can be seen under a microscope. Milk, blood, honey, and starch solutions are all colloids. Colloids are also called colloidal dispersions because the colloidal particles are dispersed throughout the mixture. For a colloidal solution, we use the term dispersed phase and dispersion medium. The phase that is scattered or present in the form of colloidal particles is called the dispersed phase, and the medium in which the colloidal particles are dispersed is called the dispersion medium. For example, in a starch solution, starch represents the dispersed phase, while water represents the dispersion medium. Colloids can be classified on the basis of the physical state of the dispersed phase and the dispersion medium, the nature of interaction between the dispersed phase and dispersion medium, the types of particles of the dispersed phase. Let us first discuss the classification based on the physical state of the dispersed phase and the dispersion medium. Depending upon the physical state of the dispersed phase and dispersion medium, 8 types of colloidal systems are possible. Dispersion of a solid in a solid, liquid, or gas dispersion mediums results in the formation of a solid sol, fluid sol, and aerosol, respectively. Colored glass and gemstones are examples of solid sols. Paint, muddy water, and cell fluid are fluid sols. Fluid sols are mostly referred to as sols Examples of aerosol are smoke and dust. Dispersion of a liquid in a solid, liquid, or gas dispersion mediums results in the formation of a gel, emulsion, and aerosol respectively. Examples of gels are cheese, butter, and jellies. Milk, hair cream, and certain medicines are examples of emulsions. Fog, cloud, mist, and insecticide sprays are examples of aerosols. Dispersion of a gas in a solid or a liquid dispersion medium results in the formation of solid sol and foam, respectively. Examples of a solid sol with gas molecules are pumice stone and foam rubber, soap lather, whipped cream, shaving foam, and froth are examples of foam. It is important to note that a colloidal system of gas into some other gas is not possible because gases always form a homogeneous solution. Since colloidal systems are heterogeneous, they cannot be obtained by dispersing a gas into another. Depending upon the nature of the dispersed media, sols are given different names. For example, if the dispersion medium is water, then the sol is called as aquasol or hydrosol, and when the dispersion medium is alcohol, it is called an alkasol. Another way of classification is based on the nature of the interaction between the dispersed phase and the dispersion medium. Depending upon the affinity of the dispersed phase for the dispersion medium, colloidal systems may be classified into two categories: lycophilic and lycophobic sols. Let us first discuss the lycophilic sols. The word lycophilic means liquid-loving or solvent-loving. When substances like starch, gum, and gelatin are mixed with the suitable liquid, that is the dispersion medium, they readily form colloidal solutions. Such colloidal solutions are called lyophilic colloids. When water is the dispersion medium, they are called hydrophilic colloids. Lyophilic salts are quite stable and cannot be easily precipitated. An important characteristic of lyophilic colloids is their reversible nature. That is, if the dispersed phase is separated from the dispersion medium, for example, by evaporation, then the sol state can be achieved again by simply mixing with the dispersion medium. Let us now discuss the second category of colloids, lyophobic colloids. The word lyophobic means liquid-hating. Lyophobic colloids cannot be formed by spontaneous dispersion in the medium, but can be prepared only by special methods. Arsenic sulfide, ferric hydroxide, gold, and other metals form lyophobic colloids. These metals are sparingly soluble, and thus their molecules do not pass readily into the colloidal state. Lyophobic colloids are also known as irreversible colloids because their residue obtained by evaporating dispersion medium cannot be converted back into a sol through ordinary means. Lyophobic colloids are readily precipitated on adding a small amount of electrolyte by heating or by shaking vigorously, and hence are not stable. Lyophobic salts need a stabilizing agent, if they are to be kept for longer times. Colloidal classification. Types of particles. You already know two ways of classification of colloids. Another third method of classification is based on how different substances that form a colloidal solution acquire the required particle size. Accordingly, colloidal solutions are classified into following three categories. They are multimolecular colloids, macromolecular colloids, associated colloids. Let us first study multimolecular colloids. As the name suggests, multimolecular colloids are formed when a large number of atoms or smaller molecules of the dispersed substance aggregate together to form a species whose size lies in the colloidal range. For example, a gold sol consists of particles of various sizes that are a cluster of several gold atoms. A sulfur sol consists of colloidal particles that are aggregate of S8 molecules. These molecules in the aggregate are held together by van der Waals forces. The other category of colloids is macromolecular colloids. Certain substances like starch, proteins, and cellulose have molecules of big size which lie in the colloidal range. The solutions of these substances in suitable solvents are called macromolecular colloids. Synthetic macromolecules such as polythene, nylon, and polystyrene also form colloids when dispersed in suitable solvents. Macromolecular colloidal solutions are stable and resemble true solutions in some respects. Now we will discuss the last category of colloids, namely associated colloids. There are some substances that behave as normal strong electrolytes at low concentration, but behave as colloidal solutions at a higher concentration. The colloidal behavior is due to the formation of aggregates of small particles. Such aggregated particles are called micelle, and the colloid thus formed is called an aggregated or associated colloid. Surface active agents like soaps and detergents are examples of associated colloids. The formation of micelle depends upon two factors: the concentration of the disperse phase and the temperature. The formation of micelle takes place above a certain concentration called critical micelle concentration or CMC, and above a particular temperature known as Kraft temperature or TK. Every micelle system has a specific value of critical micelle concentration. For soaps, the CMC is 10 to the power minus 4 to 10 to the PA minus 3 moles per liter. Each micelle contains at least 100 molecules. Micelle are generally formed by specific types of molecules that have both lyophilic as well as lyophobic ends. Soaps consist of sodium or potassium salts of HIO fatty acids and are represented as RCOO minus Na plus. In soaps, the alkyl group that consists of long carbon chain is lycophobic, while the polar group is lycophilic in nature. Molecule to lycophilic and lycophobic ends are called surface active molecules or surfactant molecules. Let us now discuss the mechanism of micelle formation. In sodium stearate, The long hydrocarbon part of stearate radical, that is C17H35, is lyophobic end, while COO- is lyophilic end. When the concentration of the solution is below its CMC, sodium stearate behaves as a normal electrolyte and ionizes to give sodium and stearate ions. These stearate ions remain on the surface of water and orient themselves in such a way that the lyophilic end of COO- dips in water, while the lyophobic part, the C17H35 part, stays away from it. At the critical missile concentration, the polar COO part is pulled into the bulk of the solution. Thus, a plaster is formed with the hydrocarbon chains pointing towards the center of the sphere, and the COO- part orients towards the surface of the sphere. The aggregate thus formed has the dimensions of a colloidal particle and is known as ionic micelle. Detergents like sodium labile sulfate undergo micelle formation in a similar manner, as the cleansing action of soaps is based upon its tendency to undergo micelle formation. The stearate ions of soaps arrange themselves around an oil droplet in such a way that the hydrophobic part of the stearate ions is directed towards the oil and the hydrophilic part protects outside. The hydrophilic part, being polar, interacts with the water molecules, and the oil droplet is pulled away from the cloth into the water to form an ionic micelle. The stearate ions of soap molecules help in making a stable immersion of oil with water, which is later washed away with the excess of water. A shape of negative charge is formed around the globules, which prevents them from coming together and forming aggregates. We can also say, soap acts as an emulsifier and helps an emulsion stabilize.